Okay, this section we will talk about the medium voltage drive, part A. So for medium voltage drive, for the medium voltage motor, the power rating is typically from 400 kilowatt to 40 megawatt. This is generally speaking, but sometimes you have big motors, which was driving by VFD. Like my company, Nanco, we build largest medium drive in the world for a 120 megawatt motor. This is kind of a 18 kV dual winding motor for the test bench. Then for the voltage, the typical voltage from 2.3 kV and to 10 kV. So the majority is from 3 kV to 10 kV. And for the medium voltage motor, the majority is fixed speed. Only about 3% is driving by the variable speed drive. And for those use the driving by the VFD, majority is by the load type is a pump, fan, and a compressor. And a very few, a small portion, the load is we call the non-standard or engineered drive, like a roller mill for the steel industry, or the some test bench. This is a typical composition of a medium voltage drive. We have the rectifier, which convert AC to DC, and DC filter. DC use a capacitor or reactor. Then the inverter, DC to AC. And sometimes, on the motor side, you have a filter. Also, most of the medium voltage drive, you have a transformer in the input side. And sometimes you need a line side filter. And here is the power supply. So we'll talk about some typical structure for the medium voltage drive. The first one is LCI. It's a very old topology. L is load commutated inverter. They use SCR for rectifier and react for in the DC filter, and also SCR on the inverter side. So because SCR, you can turn on, use the gate, but you cannot turn off with the gate. You need to put the SCR on the reverse bias on the AK, on the main terminal to get turned off. So the motor, when you run the inverter, the motor should be overexcited to make sure the current of the motor is leading the voltage, so the SCR can commutate it, can turn off. So this is why we call the load commutated inverter. They use load, the synchronous motor, to do the commutation. You cannot use induction motor for this kind of drive topology because you need the current leading the voltage on the motor side. And on the rectifier side, also use the SCR. So the power factor will be very low at the low power output. Like if the motor is run at a very low frequency, then the load is very low, and the because of the firing angle, the phase angle of the rectifier SCR, so the current on the input is lagging the voltage with a very large degree of lagging, so power factor is very low. And also the harmonic, if you use a 6 poles, the harmonic is very high. Also you can have some method like the multiple input to reduce the harmonics. And this is a typical current waveform on the output side. Okay, similar on the line side, and this is the waveform is like a trapezoidal and not a sinusoidal waveform. And this is the actual waveform on the motor side. You can see here is the voltage, motor voltage. Here is the current. current is trapezoidal, and also the current is leading the voltage. You can see the waveform. And here is the output torque on the mode side because of the harmonics. So there is a significant torque ripple on the mode side, 6 times. The ripple frequency of the torque is 6 times the fundamental frequency of the output current. And in order to reduce the harmonic, people use two set of LCI to drive the motor. The motor you can use a 6-phase motor with 2-state winding and a 30-degree phase shift to cancel some of the torque ripple harmonic on the motor side. And on the line side, you will use a 3-winding transformer. The signal of transformer will be one with Y, another with delta, and a 30-degree phase shift. So a lot of harmonic will be cancelled by this kind of multi-pulse rectifier, like a fifth and the seventh order harmonic. Majority of those harmonic will be cancelled. The only left harmonic will be, as we discussed before, will be Kp plus minus 1. And here P is 12 because of 12 pulse. So the majority of harmonics were 13, 15, 11, 13, and the 23rd and the 25th kind of the majority of harmonics. So in a lot of cases, 12 pulse still cannot meet the IEEE standard or other standard. So you will have to set an extra power filter and also power factor correction because of the power factor is very low on the low condition. And here's some comparison between the VSI and the LCI. LCI actually is a older technology and is used very few today. In some very few applications still use LCI, such as a huge drive for the pump or blower system, especially for the soft starting. Like on the blower for the steel mill, and the drive is only used to start the motor, and after start then will be synchronized to the grid and run by the grid. So drive is only running for a short period of time. So harmonic is not a big issue, and LCI is cheap. So those areas, still use LCI in a lot of cases, especially for the drive on the condition that drive will run for a long time, always running. People will prefer to VSI. So some comparison for the harmonic. So VS drive, the power factor is very good because they use diode as a rectifier. Normally, very, very low degree of lagging between the input current and the voltage. And also harmonic is good, typical VSI, I will use 24 pulse or 60, 36 or even higher rectifier numbers. But LCI, typically is 12 pulse maximum. So still very high harmonic, cannot meet the IEEE standard. So you need a harmonic filter or power factor correction. And torque ripple, VSA uses PWM technology. So output current waveform is very good, very sinusoidal. But this one is a trapezoidal waveform, so the torque ripple is very high. Power factor, as we said, because of the diode rectifier, and this one SCI rectifier because of the lagging of the current on the input side. So power factor is also low. And power system stability, big difference. And AC power disturbance, we call the low voltage ride-through function. In VSI is quite easy because you have a capacitor on the DC bank, and the rectifier is diode. And if there is power ride-through, power out or power voltage reduce, power loss, then you can use the kinetic energy feedback function as a ride-through. But LCI, because the SCR on the rectifier side, you have a power disturbance, then the SCR firing will not work, so will shut down. So it's quite big difference. And the motor VSI, typically you can use a standard motor, especially for those with the VSI with the multi-level output. You can use existing motor or old motors. But for the LCI, first of all, you can only work with the synchronous motor because you need to overexcited it to get the current leading the voltage. And also, uh, when you drive the motor with the VSI, typically during the running, when you adjust the speed, the power factor of the motor is always keep 1. So that means the current of the motor will be minimum, will lost current, and the high efficiency on the motor, and also the high efficiency on the drive, and also for sizing the current of drive, because the PF is 1, so the current is minimized. But for the LCI drive, the current should be leading, and also the pull factor is about 9.9. So you have a high current and high loss on the winding on the drive. And also for the motor design, the special design on the subtransient reactance for the motor design. So that will also increase the cost of the motor. And the reliability, both of them are reliable. And for the starting torque, LCI, because of the harmonic and torque ripple, so normally is 40 to 80 to 50%, but for the VSI is much higher. Now here is a typical outlook of the LCI drive. Here's a rectifier, AC to DC, reactor on the DC to AC control. And the second type of current source drive is we call the SGCT current source. SGCT, first we know IGCT is a kind of a power electronics device, integrated gate commutated thyristor. So IGCT is like this, with the inverse parallel diode. This is normally used in the VSI drive, but for the SGCT, it's like this. It doesn't have the reverse diode. So S is for symmetrical. Because IGCT, if you put the voltage on the reverse bias because of the conducting diode, you cannot withstand the reverse voltage. But SGCT, you can withstand the reverse voltage. So there's a difference between those two components. And SGT is also gate controller. So it's different from SCR, SGC can either be turned on or turned off by the gate signal. So it's kind of fully controlled components. And you can use a PWM, current PWM on the SCT inverter to make sure you have a relatively high frequency, and different from the SCI. LCI, SCI is like a cycle control, not a PWM control, and the output waveform is much better, and there will be a small filter on the output side. And on the rectifier side is typically also use SCR, or sometimes people will also use SGCT as a rectifier on the line side. So for SCR, you can have this topology is like eight pulse. You have 2 sets of rectifier, and each secondary you have a 20-degree phase shift, and you have a 18 pulse rectifier. So this is a current and the voltage waveform of the SGCT inverter, SCT current source inverter. And this is a typical outlook of SGC current source inverter. SGCT current source inverter is manufactured by only one manufacturer, the Rockwell. So this is all for today's section. Thank you.